Today we're going to take our transformations one step further. Instead of learning just how to multiply and divide, add, and subtract constants, now what we're going to do is add two random variables together. So we're going to start by talking about combining random variables, so adding them together. So to get my mean of the sum of the random variables, that's the expected outcome for the total, my mean of the total is going to be my mean of x plus my mean of y. Now this is pretty straightforward, but before we go on to variability, I need to remind you about independence a little bit. Remember that in order to multiply two probabilities together, I had to have independent random variables. The variables had to be independent. So independent is really important. So knowing whether one event occurs alone tells us nothing about the other event, right? So in order to add variance, and I can't add standard deviation, I need to add the variance. But in order to add the variance, I need to make sure that these are in fact independent random variables. Once I know that they're independent, if I'm trying to add two variables together, then you know what? The standard deviation is the same. But again, I can't calculate standard deviation, I can only calculate variance. So I'm going to say my variance is equal to the variance of x plus the variance of y, right? Okay, so now we're going to talk about taking the difference between two random variables. So we're talking about the expected difference. And again, I've got the mean of my difference is going to be my mean of x minus my mean of y. Now the order is very important, that you define the order and you state what it is. Is it x minus y or y minus x? That will make a difference in the problem, so make sure that the order is defined carefully. I usually do it with a formula like this. Now we already talked about on the last slide, we can't add standard deviations. You can only measure variance, so variance is what we have to add, and we can only do them when they're independents. So now we need to talk about how we do the variance with the difference. On the last slide, it made sense that if we were adding, we take all the variability of x and add it to all the variability of y. But when we're taking a difference, we actually do the same thing. We add the variance. Michelle, that doesn't make any sense. Of course not, right? But it does if you think about this. If you think about, look, we want to see overall this transformed data, what the variability is. It doesn't suddenly become smaller when we are looking at two different variables. It's going to have to be a larger range to account for the fact that we have so much variability in x and so much variability in y. So when we're calculating the variance of the difference, we add. This is tricky. Don't forget that. So now the question becomes, what happens if we multiply each of our variables by something and then try to total them? So we're transforming and we're adding random variables. The mean is kind of just what you think it would be. To get our mean of our total, we're going to multiply our x variable by the mean and then add a second, whatever we're multiplying by the y variable's constant, and we're going to multiply that by the mean. The standard deviation, however, is very different. So if you'll notice this, it's a squared times the standard deviation x squared, so times the variance, plus b squared times the variance. So what's happening here? What's happening here is we're multiplying the constant by the standard deviation, and then we're squaring it to get the variance. So you multiply the standard deviation, but then you have to square to get the variance. That won't tell us standard deviation, just variance, so then we're going to have to take the square root. So in words, remember that you need to transform with a constant, transform the standard deviation, then square for variance. So if you have to transform with a constant when we're adding multiple variables, transform the standard deviation first. So multiply the standard deviation, then square the whole thing to get the variance. If you're adding two random variables, you have to add the variance. So let's put this into practice. A lottery game offers the chance to win $500 if you pick a number with 3 digits from 0 to 9 that matches their pick of a 3-digit number. Because there are 1,000 numbers with 3 digits, you have a probability out of 1 out of 1,000 of winning. So we're going to take X to be the amount your ticket pays you. So the first step is to create a probability distribution. So okay, I'm going to say that the payoff of X, and I have a probability. So the payoff is either I win nothing, and there's a 0.999 chance that I could do that, or I could win $500, and there's a 0.001 chance of doing that. Okay, so calculate the mean is the next step. And again, this is old stuff we've done before. So to do the mean here, I have 0 times 0.999 plus 500 times 0.01. And when I do that math, I get 50 cents. Okay, is my payoff. So then now if I'm doing this next part I need to do is the standard deviation. So same as before, I can only calculate variance and then take the square root. So in this case, I'm going to go 0 minus 0.50 squared times my probability. And I'm just using the formulas that we did before for discrete random variables. So 500 minus 0.50 squared times 0.001. And when I do that, I get this to equal this, 449.75. And I'm going to need to take the square root of that in order to get my standard deviation, not my variance. And I would say, okay, that's going to be 1580 would be my standard deviation. So I'm going to put that here so that I can do this to give me enough room to do problem C. So I found the mean to be 0.50 and the standard deviation to be 15.80. So part C changes everything. It says if you buy a lottery ticket, your winnings are W equals X minus 1 because it costs you $1 to play. Find the mean and standard deviation of W, show your work, and interpret in context. So I know that mu of W is going to equal my mean of X minus my 1, right? So in this particular case, I have 50 cents minus $1 equals negative, equals negative 50 cents. So this is my winnings mean. The standard deviation is pretty straightforward. It's just addition, so I don't actually change it at all. So my standard deviation is 1580. So I haven't yet interpreted this in context, so I wrote out the context there for you. So I've showed my work, and then it says on average, when playing this game, people will lose 50 cents, and individual outcomes vary by about 1580. I guess I was a little redundant on average there, but individual outcomes vary by about 1580 on average. So we've done our work, we have showed our work, we have everything interpreted in context, we're all set. Now we've changed the problem. Suppose you buy a $1 ticket on each of 2 different days. So now each day is its own random variable. So I'm going to define my variables, and I'm going to say T equals the total payoff. Okay, X is going to be equal to the first day's payoff. and y is going to be equal to the second day's payoff. Okay, so I've defined all of my variables. So essentially I'm saying, look, my total is whatever I win from the first day plus whatever I win from the second day. And this is payoff, mind you, not winnings, payoff. So again, I'm going to say, well, my mu of t is equal to my mu of x plus my mu of y. And see, each day of the same is the same of my payoff. It should be 50 cents plus 50 cents. So if I play for one day, I should be expected to win an average of $1. And then the same is also true of my variance. So I need to add the two variance. Right, so that's going to be 1580 squared plus 1580 squared. That's 499.28. And then I'm going to have to take the square root of that to get the standard deviation. So the standard deviation of this is going to be 22.34. I'm going to put this up here again for the problem. So I'm going to say my mean of my t is $1. And the standard deviation of my t is 22.34. So now what we need to do is we need to find the mean and standard deviation of our total winnings. Interpret each of these values in context. Okay, so this one isn't so bad. So my total winnings, right, are going to be whatever the total was. Or I guess I should say it like this. My winnings is going to be my total minus 2 because it cost $2 for the tickets. So okay, I'm not transforming a whole lot here. I'm going to say that this is my total minus t. So that's $1 minus $2 is negative $1. And then since I'm just subtracting and not doing any sort of multiplication, my total for this has to equal my total for my standard deviation for my total is going to be the same as my standard deviations for the winnings because I'm only transforming with a subtraction, so it doesn't actually affect the standard deviation. So I don't even need to show my work so much except for saying that these are equal. So I can go just like that. So here it is in context. On average, when playing this game 2 days, people will lose $1. Individual outcomes will vary from this amount by about $22.34 on average. So again, this problem, not so bad. I've just added and subtracted to transform my variables and combining. Let's try a different problem. Before we go into a more difficult problem, I just wanted to reiterate this and make sure that I covered this, that when I'm combining normal random variables, the shape stays the same. So any sum or difference of independent normal random variables are also normally distributed. So as long as they're both normal, they stay normal when we add them together. So shape stays the same. All right, let's get on to that problem. So HNA's excellent swim team has an amazing 400-meter freestyle relay. Each swimmer in this relay swims 100 meters. The times and seconds for the 4 relay swimmers are approximately normally distributed with means and standard deviations shown below. Assuming that the swimmers' individual times are independent, find the probability that the total team time in the 400-meter freestyle relay is less than 220 seconds. Follow the 4-step process. If you remember, the 4-step process is state, plan, do, conclude. Okay, so state. What is the probability that the relays team's swim time is less than 220 seconds? So let's go into the plan. So we're going to say, let T stand for the total relay swim times, and X1 be Lily's time, X2 be Sally's, X3 be Megan's, X3 be Sarah's time. If that's correct, then your total is x1 plus x2 plus x3 plus x4. So then we can write that out. So then my mean is going to be mu sub 1 plus mu sub 2 plus mu sub 3 plus mu sub 4. So that's 55.2 plus 58.0 plus 56.3 plus 54.7. And then I get a total of 224.2 seconds. And then I also need to come up with my standard deviation of my total. So that's my variance, right? Variance all added together and then take the square root. Variance of x3 squared plus the variance of x4 squared. And I'll take this big square root. So it's going to be 2.8 squared plus 3.0 squared plus 2.6 squared plus 2.7 squared, and then again need to take the square root. So for that I get 30.89, which I need to take the square root of, and I get 5.56 seconds. Right? So essentially what I'm saying is this normally distributed, t is normally distributed, and t is normally distributed with a mean of 224.2 and a standard deviation of 5.56. And we're going to use this to find the probability that t is less than 220. Looks like a z-score to me. So let's do the do. So in order to do this, so I'm going to write this again, the probability that my t-score is less than 220. So I definitely need to write this out. So I have a mean of essentially 224. So this is 224. So I'm going a little bit below that, 220, and I want to know what's the probability that they're going to be less than 220. So this is what I'm looking for. So I've shaded my region. Now I need to write this out with a z-score. So I need to say it's the probability that the z-score is less than 220 minus 224.2, all divided by 5.56. Okay, so I can leave it like this if I want, and then what I can do is say normal CDF. Okay, so if you're on a TI-89, this is going to be in Stats List Editor under Distribution. If I'm on a TI-84, I'm going straight to Distribution on my calculator. So again, normal CDF, and I want to list what my lower is. Right, so in this case, my lower is negative, the biggest number I can think of, or negative infinity if you have an 89. My upper is going to be 220. My my mean is going to be, the mean of my total is going to be 224.2. And my standard deviation of my total is 5.56. So when I go ahead and enter all of that into my calculator, I get, I'm just going to enter this in here, boom, same value. So I get a proportion of 0.225 is what I get. If you were to do this with a table, I think you get 0.2236 looking at the z-score. So if you were to do this with a table, you end up with a z-score that is, I'm looking for something that's less than negative 0.76. Okay, so here's my answer. But of course, it's not in context. So in context, there is approximately a 22% chance that the relay swim's time will be less than 220 seconds. And that is that problem.
Hi ladies, so we're going to go over a couple of examples before we take the quiz. You can follow along with me on your OneNote. So it said problems before the quiz in your OneNote under the PowerPoints, and it will have the example that I'm about to read up there so that you can reference while we're going over this video. So go ahead and open that up on your OneNotes, and then I'll go ahead and read it aloud. The amount of nitrogen oxides, NOx, present in the exhaust of a particular type of car varies from car to car according to a normal distribution with a mean of 1.4 grams per mile and standard deviation of 0.3 grams per mile. 2 randomly selected cars of this type are tested. One has a 1.1 grams per mile of NOx, the other has a 1.9 grams per mile. The test station attendant finds the difference in emissions between the two cars surprising. If the NOx levels for the 2 randomly chosen cars of this type are independent, find the probability that the difference is at least as large as the value that the attendant observed. Follow the 4-step process. So our main problem here is at least as large is definitely a problem. So at least as large is going to mean that I want to know how great that difference is in either direction. So I want to know how likely it is to be less than that difference and greater than that difference. I'll show you what I mean on the next slide. Okay, a difference of at least as large, right? So that's kind of a crazy concept. Again, let me talk about that. So I'm saying that my difference, it could be this, or my difference could be this. So what I'm talking about is really the difference in either directions. So either my difference is this, and I end up with a negative 0.8, or my difference is this, and I end up with a positive 0.8. So I want to know what is the idea that the difference is at least 0.8. So the difference is 0.8 in either direction, really, so I want to look at it in either direction. So I want to see, okay, what's the likelihood that it could get 0.8 or be larger than 0.8, or what's the likelihood that it could be negative 0.8 or less than negative 0.8? So I want both of these things at the same time. So this is really, I'm looking at two sides. We would call this a two-sided test. I'm looking at two sides of the probabilities, not just one this time. So I'm going to have to find out what this side is here and add it to what this side is. Okay, so the state is, what is the probability that the difference between the NOx levels for the 2 randomly selected cars is at least 0.8 grams per mile? And then remember that I wanted as great as, so it could be 0.8, it could be greater than 0.8 or less than negative 0.8. So we need to look at both directions. Okay, so just so we have the same reference point, we're going to say car 1 is X, and that was 1.1. And we're going to say that car 2 is Y with a 1.9. Great, so our plan. So we have a normal distribution, and we need to find what the mean and the standard deviation are of our normal distribution once it's transformed. So we need to find the difference of x minus y and the difference of y minus x, right? Because we want to do it in either directions. So if I do x minus y, we have a difference of negative 0.8, and then here we have a difference of 0.8. So essentially, that's the difference that we're looking for. We did that earlier, so you could see why we did that. And then I want to talk about the mean. So the mean of the difference is going to be my mean of what x should be minus my mean of what y should be. Now the mean was given to us as 1.4. So both cars should have a mean of 1.4, and they should have a standard deviation of 0.3. So if I go 1.4, it's 1.4 minus 1.4, hey, guess what? It's 0. So my mean of my difference is 0. The standard deviation, however, I'm going to need to add my variance. So 0.3 squared plus 0.3 squared, take the square root of both sides, and I'm going to end up with a standard deviation of 0.4243. So I have a mean of 0, a standard deviation of 0.4243, and what I'm looking for is the probability that x minus y is going to be less than negative 0.8, and, big and there, the probability that y minus x is going to be greater than 0.8. So if I'm drawing a picture of that, again, like we did on the other screen, I would say that this is negative 0.8 and this is positive 0.8, and I am looking for both of these added together. Okay, so I'm going to write down the z-score. So my difference was 0.8 minus 0 divided by my standard deviation of 0.4243, and then I'm just going to use TEC. So using TEC, I'm going to say that this is my lower, in this particular case, was 0.8. My upper was infinity. My mean is 0, right? And my standard deviation is 0.4243. Okay, so then the other side is just the same thing. My lower is negative infinity. My upper is negative 0.8. My mean is 0. My standard deviation is 0.4243. So when I find this using TEC, I'm going to find that this is 0.02968 and this is 0.02968. So when I add them both together, I get an answer of a total probability of 0.05936. Okay, so the conclude for this says there is only about a 6% chance of randomly finding two cars with as big a difference in NOx levels as the attendant found. So then there's our conclusion in full context. The last problem I wanted to quickly go over dealt with a problem that you probably saw in the sapling last night that might have stumped you. A study of working couples measures the income X of the husband and the income Y of the wife in a large number of apparently heterosexual couples in which both partners are employed. Suppose that you knew the means mu sub X and mu sub Y and the variances sigma sub X and sigma sub Y of both variables in the population. A, is it reasonable to take the mean of the total income X plus Y equals mu sub X plus mu sub Y? Explain your answer. The answer is yes. The mean of a sum is always equal to the sum of the two means together. So we're good. That one's fine. B, is it reasonable to take the variance of the total income to be the variance of X plus the variance of Y? Explain your answer. The answer to this is no, because the variances of the sum is only equal to the sum of the variance when X and Y are independent. So I can total up the sums and have them not be independent, but I can't do that for the variability. So we can't assume that there's not some impact of X on variable Y or Y on variable X. These incomes may be related, especially since they're a couple, so we cannot say that they're independent. And that's it. You are now ready to take your quiz. You got this, ladies.